Hi there, this is a video about stepper motors. At the top of the screen here we see a stepper motor. So cool because it's capable of moving in incremental steps. I've written a program on this microcontroller that moves it in clockwise direction and then in anti-clockwise direction. First in slow steps and then in fast steps. You can control the steps very precisely. You can just move one step if you want, or you can move many steps. You can move in either direction. So that is a stepper motor. Very useful for robotics, for kind of things like making 3D printers or plotters or anything where you need to move precise steps. So how does it work? Well, allow me to explain. If you take a coil of wire and wrap it around a nail, you create an electromagnet. So I've got a nail here and I've wrapped a coil of wire around it. If I then connect this up, first of all show that it's not a magnet. Not a magnet at the moment. If I just connect this up to a battery, I have an electromagnet. So a coil of wire around a piece of metal creates an electromagnet. So it's an essential piece of information we'll need in a minute. This is a logical diagrammatic representation of a stepper motor. What it comprises of is a permanent magnet in the middle, and here's its north and south pole surrounded by 4 electromagnets. So all these are a ferromagnetic material like iron with a coil around it. If we energize the coil, we create a magnet. That magnet will have poles, just like a permanent magnet. The pole orientation will depend on how we set up the positive and the negative terminals. If we set them up like this, then we'll get repulsion between the permanent magnet and the electromagnet, and the permanent magnet will want to move away. If we set them up like this, then we will have the polarity of the magnet will look like this. And the north and the south terminals will be attracted, and the permanent magnet will be attracted towards the electromagnet. We only really care about the pole that's nearest the permanent magnet. So I'm going to ignore the outer pole from now on. Now, the pole that's nearest the permanent magnet will be determined by how we arrange the current flow, which is the polarity. You'll have to trust me on that. I haven't got a demonstration of that. If I wanted to demonstrate that, I'd need a couple of electromagnets and show them repelling each other or something like that. But trust me that it's true. Now, we arrange these coils, these electromagnets, in pairs, so that actually these are connected in pairs. So that when I energize this one, I also energize this one. And when I energize this one, I also energize this one. I'm going to call this A, and I'm going to call this A prime. And the reason this is called A prime, this is a typical notation used to mean it's the opposite, is because this will have an opposite pole orientation, which means that when I energize A and A prime, we'll just call that the A pair, in a particular direction, whatever the inner pole is on A prime will have the opposite pole. And if I was to switch these round, A prime will have north and A will have south. And the same is true of our other pair, which we're going to call B and B prime. So how do we actually step the permanent magnet round? You're probably already getting some idea. What we want to do is energize the A pair first, and then energize the B pair, and then energize the A pair again, then energize the B pair again, and then energize the A pair again. But there's something important that we need to do when we do this. So first of all, we energize the A pair. The actual pole that's created will depend on the polarity, and which will in turn depend on which way this has been coiled around the metal. It doesn't really matter, but just assume that in this orientation the south pole is here. Because we have attraction between the permanent magnet in the middle and the poles of the electromagnets, we will be fixed in this position. Now the next step along, we want to energize the B pair. Let's assume again that this orientation means that this is a south pole and this is a north pole. What will happen, because opposite poles attract, the rotor, which is the thing in the middle, will rotate round. Now we want to energize this again. If we were to energize it in the same configuration as before, which if my memory serves correct was plus and minus like that, then we'll have the same pole orientation, which means we'd go back to there. We would have gone backwards. So what we actually have to do is energize it in the opposite direction, so that our poles are reversed and we end up with south down here, which means we carry on rotating round in a clockwise direction. Now we have to energize B again, and again we don't want to use the same polarity as before, otherwise we'll just go back. So we switch the polarity again, which means that south is here and north is here, and we rotate round again. Now to get back round to the beginning, we energize the A pair in its original configuration, making this a south pole, this a north pole, and there we go. Back to the beginning. So essentially by energizing the A pair, then the B pair, then the A pair in the opposite polarity, then the B pair in the opposite polarity, then the A pair again, we get one full rotation. If we want to go backwards, we energize the A pair, the B pair in its opposite polarity, the A pair in its opposite polarity, the B pair in its normal polarity, and then the A pair again. So that's how we can control the rotation of the permanent magnet using the electromagnets and by changing their orientation, their polarity. We can also do some things like energize A and B at the same time, so that they're both south poles, and then these will both be north poles, and we'll kind of hold the magnet like that, and we can do the same and rotate round like that if we want. Or we can energize it so that we're attracted to these, and then like that, and then like that, and do what's called half stepping. There's lots of different ways, well there was a few different ways, not a lot, to energize the coils to rotate the permanent magnet in the middle. But that in principle is how it works. In a real stepper motor, there will usually be more coils, and then the coils will be magnified using a mechanical kind of contrivance by adding teeth onto the rotor and the stator, which is the outside bits. And by having teeth, you essentially create more poles. Even though you've got only 4 physical poles, you might create, by having 4 teeth on each one, maybe you end up creating 16 effective poles. So you can increase the step resolution by having teeth on the poles. But we're not going to go into that in any more detail today, because I don't know exactly how it works. I need to take apart a motor to see precisely how the teeth are arranged. but you can imagine that it works, and it does work because people have done it, and you can find a motor where it works. Now, so what we need to do if we want to drive this is we need to be able to control this coil. I'm going to call this a single coil because it's connected together, so effectively it is. And we need to be able to control it being either on in one direction or on in the other direction, or off. So how do we do that? Well, if we want to connect it up in one direction, we would wire it up like this, down to negative. If we want to connect it up in the opposite direction, we'd wire it up like this, and we'd get rid of that. But we want both. So what do? We connect it up, and we put switches in here, 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 and here. Then if we want current to flow in one direction, we turn on this switch and this switch so that current will flow through here. You obviously can't go down that path or that path because those are off. Or if we want it to flow in the opposite direction, we switch this switch on and this switch on so that current flows in this direction. So that's pretty straightforward. And this configuration is called a hedge bridge, which uses 4 switches to control the direction of current through a component, in this case a coil. It's called a H bridge because it looks like a H. In order to control 2 coils, so our A pair and our B pair, we need 2 H bridges, one for each pair. We can construct H bridges using either relays, MOSFETs or transistors, and I'm going to use transistors, and I have used transistors over here. So you should be able to actually see, you probably guessed where the H bridges are now just by looking at this and looking at the previous diagram, that these transistors form one H and these transistors form the other H. So if I want, and the way that they're connected up is these 2 outputs here, which are in between each of these transistors, go to one of the coils, one pair of wires, and these outputs here, which are from the middle of these transistors, go to this other coil, this other set of wires. So that's exactly how we had it in the diagram. So if I want this first coil to be in a particular orientation, then I can turn this transistor on, this transistor on, and leave these 2 off. That means that current can flow through here, around through the coil, and then out here. If I want it in the opposite polarity, then I switch that on, I switch that on, and I switch those off, so that current flows through here, through the coil the opposite way, and then out through this transistor to ground. So that means I can control the polarity of this coil, and with this H bridge I can control the polarity of the other coil. What you'll notice here as well is that we have diodes. And the diodes go from the negative terminal of the transistor, the emitter, back to the collector, which is a positive terminal. Essentially, if we imagine the flow of current coming from the top here, this positive bar, down through this bridge, the diodes allow current to flow back up to the positive bar. The reason this is required, these are called flyback diodes or snubber diodes. Now it's easy to understand this in the context of, say, a relay or just a coil. If we didn't have a transistor here but we had a coil, then what will happen is whenever a magnetic field collapses, it generates a current. Because the action of magnetizing and demagnetizing are kind of opposite commensurable actions. So it takes energy to create a magnetic field, and when a magnetic field collapses, it releases energy. So whenever we switch off our motor, or we have a collapsing magnetic field, this pushes electrons back into the circuit, which causes a build-up of electrons, causes a potential difference, and then causes current to flow. Now, if we don't control where that current goes, it can go anywhere in the circuit. And because it's can be a potentially high voltage because it's kind of a burst of a few electrons, then we could damage some of the components, because these are only rated at, say, 5 volts or whatever. In this case they're not, but let's imagine that they are. And if we suddenly had a spike of, say, 10 volts or maybe even higher, depending on the power of the magnetic coil, then we do not want that to go through either our transistors or our circuitry and fry it. So typically what we then do is have these diodes which allow the current to flow back up to the positive terminal. So especially if we switch off, say, this switch off all these transistors, the coil is actually connected up between them, so it can't actually flow down into the circuit anyway, but it can try and flow across the transistors, and so it could damage them. But with these diodes in place, the current will flow back up to the power supply, which means that, and then that current will be dissipated because the power supply is connected to everything else. So that's to avoid damaging the transistors in essence. But you will see these flyback diodes or snubber diodes wherever there is a magnetic field that can collapse, so on a relay or something like that. And if you measure this with an oscilloscope, you will actually see the spike if you do not put the diode in. And with the diode in, you'll still see a spike actually, but it will be reduced. So this is the H bridge, and this is called a dual H bridge because we've got 2 of them, and that's used to control the motor. In this case, I'm driving it with an AT13A, which is a little microcontroller with a few inputs and outputs pins, and I've connected it to a 595 shift register. Shift register has 8 outputs, so I can control each of these 8 transistors. And of course, by designing whether they're on or off, the sequence of the on and off pulses, I can control exactly what I want. And in this case, what I'm actually doing is these 2 are on first to drive current through the first coil in polarity 1. Then these 2 are on to drive current through the second coil in polarity 1. Then these 2 are on to drive current through the coil in polarity 2. And then these 2 are on to drive current through the second coil in polarity 2. And so that would be a pulse of, if you imagine your 8 outputs. So to begin with, we just want these 2 on. The way I've connected it up, that would be 1 0 0 1 0 0 0 0. But anyway, so you can imagine you can easily design the pulse train to switch these on and off. And I've done it. I've written a little software library so I can control the steps and the direction and so on. Okay, that's it. Hopefully that wasn't too garbled and you've understood a little bit about how stepper motors work. Maybe in a future video, if I can, I'll try and take apart a bigger stepper motor and try and provide some explanation as how the mechanical contrivances of the teeth allow for an effective higher resolution. Oh yeah, one more thing. This motor has 20 steps, so that's 360 divided by 20, which is 360 divided by 10 would be 36, divided by 2 again would be 18. So it has an 18-degree resolution, 20 steps. Alright, well, that's it. I'm no expert on this, but if you've got any questions, let me know. I'll try and answer them. But really, I just made this video because, I don't know, someone might find it useful. So I hope you did. Alright, cheers.